Good morning, everybody. Thank you for joining our webinar today, Sound Solutions, Mastering Acoustics in Modern Timber Construction with Rothablast here. On another webinar Wednesday, my name is Chris. I am the marketing account for Rothablast here in North America, so the United States and the Canadian subsidiaries. So I just want to welcome you again back to our webinars series. If you have any questions at all throughout the presentation, we'd love for you to put a message into our Q&A section on a computer. On the top bar, you'll see that Q&A button to go in and type. And if you're on a phone, on the bottom right-hand corner, you should see three dots that opens up the menu where you can also access the question and answer. So without further ado, I'm going to pass along the presentation over to our speaker for today, Mohammed.
Thanks, Chris. Good morning, everyone. Welcome to our webinar. My name is Mohammed Badruddin. I'm a local technical engineer in Canada, and today we are presenting our webinar about sound solutions, mastering acoustics in modern timber construction. So as we know, to achieve a successful project, it's really important to adopt multidisciplinary approaches, and the acoustic design is one of them. So at Rothoblast, we recommend different components technicians and of acoustic design and for direct sound transmission and choke of materials. So if in the project if the project requirements allows, so it's always preferable to choose some constructions that they already have been tested in the laboratory, so we know their sound insulation performance. And the other subject today is the reduction of flanking sound transmission. So we will talk about the structural elements, how we can use an appropriate calculated resilient profiles, and the last is about the attention to details. So it's always important to ensure the airtight constructions to limit the airborne and sound to transmit through cracks or opening, and that can contribute to decrease the sound insulation performance. So at the beginning, we will start the flanking sound transmission. So here we can see one of our interesting products is the xylophone, is the elastic interlayer. So we have it used in different projects, as we can see here in CLT projects, and mainly like wood structures or frame structures in US, in France, in Vancouver, in Canada, and Wildwards. So we will start a bit about some intro about what's the definition of flanking transmission, and we will introduce our solutions and how you calculate your product. So I will start with a question: is the laboratory results and on-site are identical? The simple answer is no, because in laboratory, as you can see here, that we have controlled conditions. So we always measure the direct sound transmission of the separation, whether it's wall or floor. And in our case, as we can see, when we represent DD, that's called direct. So we measure the actual sound insulation performance of the separation. However, when we go on site, it's not really perfectly controlled as laboratory. So we can see that there is, including the direct path, there is different paths, what's called indirect or flanking sound transmission. And in simple walls, that the sound can transmit from wall to the wall, FF, when we said FF, like flanking, and from the floor or the separating element to the another wall, that's called direct flanking, and of course with floor, wall floor as well. So we can see that in different sides. For example, if you had a typical wall, we have two rooms that each side there is a three flanking sounds, and if we have like four sides, so that number of the indirect path, that there are 12 direct paths. And those can, if they are not properly designed, that cause decrease the sound insulation of our assemblies. Usually, we represent the sound insulation performance on site as ASTC, aberrant sound transmission class, and it's the combination of the direct transmission of the actual or assembly or separation plus the flanking sound for each edge. So each edge, as we said, there's like three paths. So all of that should be included in order to be able to identify the right sound installation performance on site. So the sound installation performance for flanking on edges is highly dependent on what's called KIJ or vibration reduction index. And this is when we have this number is high. So when we said like we have higher KIJ, that's mean better. So we have the junction of the edge here can absorb energy, and of course we have like better sound insulation performance. So usually we have, this is like if we didn't put any interlayer, and this is the case when we have an input layer. So we will decrease the flanking paths, and only the direct path will be controlled in our case. Just a small theory about how we calculate KIJ, flanking vibration reduction index. So usually it's the differences of the mean velocity level differences between two elements. For here example, we have floor and wall. So we excite the floor and we measure the vibration level velocity level differences in the same time, simultaneously between those types. And it also depends on the equivalent of the length, absorption length of the elements. So this is how we measure it. And it's really important that's to be measured or taken into account in order to know what's the actual performance of your design. So here we can see that's usually when we have a floor or a separation, it's really important to have not in one case, in one edge. So it should be for all edges controlled by interlayer. So we can decrease the flanking sound or indirect sound. And that's always have a positive impact on the sound insulation. So we will talk about, just like in the previous investigation, it has been shown that the KIJ or the vibration reduction index depends on the test setup. And in the market, there is, or in general, there is a lack of common standard. There is like an indication how to measure it, but there is not common standard how to identify the performance of elastic interlayers. So each manufacturer provides KIJ values without explain in detail the test build-up and the fastening systems, type of elements and the thicknesses and etc. And of course, this is have like a high impact on the site. For that, Rothoblast, we financed a research project aimed to measuring the KIJ or vibration reduction index for different CLT panels joints. So in this case, we identified different CLT thicknesses, and as well, we provide the details of number of screws, their diameters, and spacing between them. And also we identify the number of brackets or angle brackets and connectors, how we connect those junctions, and the influence of xylophone, or like in our product, elastic interlayer. We have like different product, and we will go through how we choose the right one depending on your case. So the objective of the project, because as I mentioned, the flexible interlayers are not currently covered by and harmonized standard. So and there is no European, neither like Canadian or US documents that specify how to have like information for flexible interlayers. So the motivation of the project is to analyze and characterize of the resilient profiles, in order to have data sheets that can provide an accurate and transparent results. And in addition, which is really important, we also in our measurements, we applied a load on those resilient profile in order to simulate the real state, because like on this, when we have like a measurement, so on the side there is like a dead and live load, there is an occupant. So that's also an effect on the performance of these resilient channels, and may not have the same results that was written in the data sheet. So here's one of the examples. We have an X junction And usually to represent the vibration reduction index, we refer a number for each side. So here, floor 1, 2, 3, 4. So when we said 1, 2, KIJ 1, 2, this is the vibration reduction index, or in the junction or in the direction of 1, 2, floor, wall. And this is the case. So we have in both junctions, X junction, we used HPS screws, step with a step 400 millimeters. So with no resilient profile, and we have construction ceiling. So we can see that, and we put it just like here in the intersection, or like on the junction. So we have like an up to 3 or 4 decibels improvement in the sound and the vibration reduction index. Another measurement was done about L junction. You can see wall, for example. So there is no resilient channel, resilient profile used, and the only thing is used is we increased the step between screws here. So we can see that just increasing those steps, that we have almost like 2 or 3 decibels better on vibration reduction index. And this is if you want just like to discuss that, this is usually when we have when we increase the steps, that can be reflected in another way, that we have less rigid junction, and the vibration can be dissipated, or the energy could be dissipated through the junction. So we could have improvement. While when we have like rigid or like more screws, that could also affect. So all of that, it wasn't just like some solutions with interlayer. So we included as well the effect of the screws, the connections with the with elastic interlayers, and the distance between screws. So, and another interesting results here, we can see we use the HPS, which is partially threaded screw, and we use VGZ, which is fully threaded screws. And we can see here that we have almost 4 decibel improvement without no resilience and nothing. And we can see that we can just have a comment here, because when we have partially threaded screws, so their job is just like to tie up the elements together, while the fully threaded screws, we have like connections without necessarily tightening them up as partially threaded screws. And this is can also, when you tied them up, they will be like close together and tied them up, and the vibration could be transferred easily, and that's you of course like you will decrease the sound installation performance. And you can refer also to our manual for xylophone. We have an interesting one. We provide many details. For example, here an L junction and T junction. So we provide the thickness, the length and the width of each floor and wall, and the fastening system as well, and the type and name of the xylophone as well. And we calculate the KIJ. Here we can see when we use an xylophone 35 with fastening, so we can see that there's an improvement. The KIJ is 13.2, and so on. And for the projects, we also published different articles, just like to prove our result, and to provide how we did all the measurements and the setup. So we can go either to our website or the published articles to find out more details. So our product is called xylophone. We have different type and different lines, and each line depends on the load, on the applied load on that junction. And we for example, with xylophone, we can reach up of an improvement of 7 decibel for KIJ. And it depends on each structure and each junction and the details. Here we can see that's mock-up setup. So we have X junction. So we identified like a CLT. So we have 2 angle brackets and 6 partially threaded screws, HPS. And we use the xylophone 35. and we also applied the self weight of the structure, because this is, as you said, this is really important, because on the reality there will be self weight and of the structure. This is going to affect on the results. Here we can see that, as we said, like we represent each floor and wall with numbers to identify. Here we can see with and without xylophone, there is an improvement of 3 decibel, and for your junction 1.4, and as well for 1.2 and 2.4, like horizontally. So we can have an improvement up to 6 decibel, 5.8, almost 6 decibel. And we can see like after that, there will be better results. And it depends really on the fastening type and the resilience profile and the loads applied and all of that. Here's another example for T junction. We used xylophone between the floor and the wall, as we can see here in the junction on details. So the same thing, we use 6 partially HPS threaded screws and 2 angle brackets and xylophone 35. So we can, and we applied a load as well. Yeah, so we can see here there is like an improvement for 1.2, for example, when we have an xylophone in between, there was an improvement up to 10 decibel, which is high, and with achieving those results, so you will be sure that you minimize the flanking transmission, and we can know that your assemblies, or like your traditional assemblies, can be performed without many differences on the data sheet or the sound installation performance. And again, in the model as well. So we identify different type and different cases, not only. So we have when we have an interlayer just for upper part, and we have an interlayer upper and lower part. And we have, as we can see, that we have like all the results for different cases. And we can see in some cases we have really like high differences, like 6 and 7 and 10 decibel even for junctions. So here's a part of the study as well, because it's important to know that many products in the market have been tested to determine only the dynamic elastic modulus and dynamic factor. As you said, since there is no common standard, so each manufacturer follows different procedures without clearly identified what the test up and how is everything was done, and the fastener system. So in our test, xylophone is subjected to static and quasi-static loading. So the dynamic elastic, as we said, is not only represent of the actual behavior. So it's also important to test the compression of the elastic interlayer. So here's the compressive modulus. In our cases, we have different type of xylophone, and this is number referred when we have like higher number, we have like higher compressive modulus as well. And here's the output for static loads. So we identify the transmissibility, attenuations, and deformation as well. And for the dynamic elastic modulus, we also carried out a test. So according to ISO 4664, part 1. And it was, we follow the test condition for a small size test. And also the material is intended to be subjected only to compression, which is also, we took it into account. So here's our results for different hertz for 1, 5, 10, and 50 hertz, the dynamic elastic modulus and damping factor for each xylophone, for each one or all of these products. But in the manual, we provide those values, and in the same time, we provide a direct, straightforward method how to use them, as we will discuss later. So here's the output of the dynamic load as well, 5 hertz. So we used for the deformation, transmissibility, and attenuation as well. And as we said, it's really important to take into account the compressive test. So the compressive set for each of the products. So all of the products, they have 6 millimeters. So the highest compressive set is like 2%, just only 2%. This is when if you use the xylophone 90, while it's like less than that. So it's really important because it's from a static point of view. It's important to provide the compressive strength as a function of the strain. And because that's also help to limit the maximum deformation and possible structural failure as well. We also could take into account the friction, because it's could one reason. So it's that could have different results in the measurements. So here we can see it depends on each floor and each load. Here we can see that we don't have a high much load, so we use xylophone 35. While in the first floor we have all the load from all the from the previous the higher stories, that we use xylophone 90, which is more rigid. And so because the point is, we don't need to use an xylophone not really rigid or not having compressive strength, and we don't use to be smashed. So when it's really compressed and have a higher load than it's recommended, so we will have a rigid connection, and the xylophone will not help. So it will not help in reducing this flanking sound transmission. So it's really important to use direct xylophone with appropriate your load, in order to use it to have the results indicated in the manual. So here's the compressive strength and deformation for 1, 2, 3 millimeters for each xylophone we have. Here's what we said. It's necessary to focus on the operating conditions, and because the goal, not only the ultimate limit stays, because this is because the goal of for insulating the building from noise during the normal operation conditions, and not during the design. Because like on the real life, there will be a dead load, and the building will be occupied, or this building will also have additional load. So usually it's really this formula depends on each regulation for each country. So usually we have a coefficients for dead load, and you have a coefficients also. So you have to include the life load as well. Just like to know the appropriate. And then in our manual, so you can see here the acoustic loads for each for each product in our case. So you have to calculate the load transferred from wall to the floor or the junction. So this load should be also calculated in Newton per square millimeters. And in this case, you can choose which xylophone is appropriate for you. Here's some tests for xylophone 35. So as we said, we have a different type. So we have here like a T junction when we use xylophone upper part and lower part of the floor, and just when we have xylophone and upper part, and for X junction as well when we use it in upper and lower part. And we can see there is always an improvement in sound on vibration reduction index. So there is up to 7 decibel. I mean, yeah. So you can refer to our manual to see in which case you need, and what's the thickness of xylophone and the fastening system as well. Here's another case. We use a T junction, yeah, with an upper and lower xylophone. And as we can see, there is like an improvement, sometimes up to 10 decibel. Yeah, in this case, we use a CLT 100 thickness and wall as well, and we use xylophone 50, and yeah, so we have and we have all the applied load. So in our manual, there is like all the information needed to have this. So we have like the fastening system, the type of the xylophone, and all the information, all the improvement and sound solution could be have when you apply the elastic interlayer. So the flanking transmission on site, as we know, that's a predictive study for the sound insulation of airborne and impact sound in the building cannot be determined only by calculation because it's always there is more factors that included could be on the on-site. So the calculation are always not usually enough to have the appropriate or the right sound insulation performance. So in our case, we have a laboratory in Innsbruck, so in Sweden, if I'm not mistaken. And we have here the upper layer, the upper floor. So we can, it's like you can rise it up to 30 centimeters, and you can use as well the xylophone, just like to have a junction with the xylophone to test the performance of the assembly. So we also like test the performance of KIJ, and we also how this will affect the sound insulation performance. And also in this test setup, it was a load was also applied. So, and in this section, as we said, the apparent sound transmission class for an assembly is determined by the direct sound transmission of an actual separation and with all the flanking sound for all edges, and which is highly depends on the KIJ or vibration reduction index, depends also on our product xylophone. So as we can see, test for the test, we have like an xylophone and up, and we have just down, and we can see that there is an improvement on total performance, because like in this case, we didn't just only calculate the flanking transmission, we calculate all the performance of an assembly. So there was like an improvement of 5 decibel, including the direct path and the flanking path, or like yeah. So there was like 5 decibel and 10 decibel. And here as well, this is for airborne sound. And when we included the impact sound, there was like an improvement of 7 to 8 decibel. 7, this is in euro, and we have it like in our Delta IIC impact insulation class, there was like an improvement at 8 decibel in each case when we use the xylophone. Here's some tips how to use xylophone, or some recommendations. So always when we have a junction, when we have a wall with the floor, so always the junction or the sides should be treated. So in this case, we can see there is the flanking path transfer from the wall and floor to the another room. When we use one xylophone, we eliminate just only 2 flanking sound, while there is like another flanking sound that can transfer from floor to wall. And the same is here when we just like under the floor. So there is like another flanking from floor, wall to floor. So the right way is just like to use an xylophone under an upper part of the floor. So here you can eliminate all the flanking sound, and we can improve the sound insulation performance in your case as well. And we at Rotoblast as well invested in the development of solutions. So that follows a multidisciplinary approach. So we take into account the durability, the static test, the moisture control, fire performance of the xylophone. We don't just provide only acoustic performance, while all of these were also tested, and we have information about that. So we performed static performance. So it was the results showed that it has a long-term behavior. And this is important because, as we said, from static review reasons, to avoid deformation further in the structure, because when we have a structure decided, so we have like a tolerance to limited tolerance, so we don't need to have additional deformation because of our products or the elastic interlayer. And for another thing, why it's important for acoustic reasons, because a crushed interlayer does not have the same elastic response, and consequently, the acoustic performance decays. As well, we have in the manual, we have over than 250 tests. We tested not only the sound installation performance of xylophone, but we tested our fastening system, including and without the xylophone. Here we tested our screws, for example, HPS screws, and we have an xylophone as well, and we have all the results. So this element is not so our interlayer is not tested just for sound insulation measurement. So we have as well like static performance, and as we can see here, also the deformability versus comprimability. So the xylophone products, so there is under the compression, there is no change in the volume, whilst the foam products, they have, as we can see here, that they have a reduction in the volume. So it's a stable product, and there is no for long-term behavior as well. For fire resistance, so as we know, that's the awareness of fire design is increasingly in Canada and US and over the world, all over the world. So in Rothoblast, we use the characteristic performance for fire resistance. So we can see here that our results indicated that after 60 minutes for exposures, the temperature of the unexposed surface remained about the room temperature, showing no color changing. And the most important thing, that the xylophone do not contribute in the fire. So it was they didn't. There was not there was not decay in the performance more than the CLT, and it did not performs in the fire as well, and reacted with the fire. And this is really interesting because like we have to take care of the fire performance. And this is a project, it was like a research project. It's called Fire Safe Implementation of Visible Mass Timber in Tall Buildings in Sweden. Yeah, so we have like the failure or like AI, up to the experimental test showed like there's like 90 minutes resistance of the performance of this assembly for CLT and including xylophone. So here's the test setup. We use test setup with here, as we can see here. Yeah. So we have like a big opening, and we have two ventilation opening, as we can see, and we have in this case, and we have 6 large opening as well. So we have all these measurements, and just for fire resistance to know how it performs. And it wasn't just like xylophone, so we have different type for fastening as well with our products. So all of that here we can see that's connecting floor and connecting floor to wall with xylophone and a fastening system. For the sustainability, we carried out an environmental product declaration, including life cycle assessment, for study all aspects related to the production. And it's important here to know that this is voluntary in any step. So there is no obligation by the law, but we have to decided to implement, just like to know the environmental impact of our products, and to allow the designer to have an idea of the ecological footprints of the products. Now we will talk the second part of the presentation is about direct transmission on timber elements. As we said, in the first part, we talk about flanking transmission and how we use the xylophone, and we saw the different types of xylophone and how what tests are performed. And today, the second part will be about the direct sound transmission. We'll present different assemblies with different solutions with using Rothoblast products, and we see how the sound installation performance. So here we can see for a wall, we have a CLT. So using a silent wall, or silent underfloor, just on the joist, on the top of the joist, we can have improvement of 13 point delta STC. Here, for example, another facade, CLT facade. So we just use a gyps band just on the outer joints. So there was like an improvement as well. So we provide like different assemblies with their sound insulation performance. Another product here as well for framed without supporting wall. We just like used an additional layer of silent wall. So there was like 6 points improvement. And here another solution as well. If you want to have, yeah, we just like added silent wall and gyps band. So silent wall was like in the outer layer after the gypsum board, and that's the gyps band just like on the outer or the inner joints. So we have improvement of 6 points. And they are really like easy to use, can be like straightforward to be used. And also the products can be as well. So for upgrading or like improving the sound insulation for existing products, for existing assembly. So here we can see that's we have a wall. It didn't have a sufficient sound insulation performance. So we're just like adding silent wall beton. So we have an improvement of 7 decibel, and we have double. We have could reach of 8 decibel. Another solution could be like implementing the sanded floor if there is a wall directly on the wall. So we can like have it, and we have like a gypsum board just like to cover it, and we can have up to 6 decibel with one layer, or up to 10 points, sorry, up in the double layer. So just like here to say like in the ASTM, when we the STC, it's represented by points, not decibel, but it's roughly like yeah, so it's roughly like the same RW and STC in most cases. And here we can see another solution. We just like add piano. It's like a strip here, just like on between after the studs, and we can have up to 9 or 13 decibel improvement. So which is really like interesting. There you not need like just like you can upload or upgrade your wall to have a better sound insulation performance. And another thing that's it's really important when we have a partition, that's the sound proofing or sound insulation of a partition is strongly influenced by the performance of the weakest elements. So in the cases of facades, for example, it could be a window or a door. So it's really important to use an appropriate ceiling for that should be wind tight in the wind tightness level, and thermal and acoustics insulation level, and as well air tightness level. So in Rotoblast we have different types. We have a hermic foam, as you can see here, that's 10 millimeters, that could have for just a ceiling, a floor, or a window, you can have up to 63 decibel. And we have another one for if you want like a fire ceiling silicone as well, and a window band. So here we can see that if you have like a wall, and if you have like some opening here, like at the end, it's not continuous. So when you add a fire ceiling silicone, that you can improve it from 25 to 49. So that's impressive, and that's really interesting, because like this is acoustics. Small cracks or small openings could have a really negative effect on the sound insulation performance. So it's really important to take all of the details. It's not just like adding the mass to improve the sound insulation, but paying attention on the details. And here's some as well. Here's some solution, or like some projects where we can see that's silent floor on the CLT in England, and the xylophone were used as well. Yeah, and there's like in Canada, in Ontario as well, and USA. So it's really like yeah, useful on site, and to be used, that's to improve your sound insulation performance. For floor sites, here we can see that if we have like a CLT with double screed with the false ceiling, just having a silent floor could have up to 7 decibel of STC, like a sound transmission class, and for impact can had up to 13 points as well. The same here, if you have like another, we could have 412, and this is like the standard floor usual. Like this is really important to have resilient underlayer or under the concrete floor. So it helps really like to absorb the energy of the impact sounds, and we could have yeah, so you could have here we can see that you have like 50, and just like using the silent pure, it could be up to 62 points, which is really which respect the code, and we and respect the acoustic comfort of the occupants as well. Another things could be do as well if you have a raised floor with here joints, and just using an xylophone or like piano or granulo just on the joist. So this is could be like it could absorb the vibration and improve the impact sound insulation performance up to 7 points. So we can see just it's not like about adding mass or like adding insulation. It's really about paying attention to the details. And here another common solution if you have like a concrete chopping and CLT. So it's always it's important to separate it by a silent pure or like a resilient interlayer. So we could have up to 10 points. And as well, upgrading the floor, if there is like a floor already there and you want just like to improve the sound insulation performance. So here we can see that they have like a joist floor, and you want to improve the airborne and impact sound insulation, just like adding silent wall beton just under the ceiling or and above the plasterboard, so you can have up to 8 points of airborne sound insulation for sound transmission class and up to 17 points of impact insulation class. Here another possibility as well for joist floor, which is common as well in Canada for residential buildings. So if you want to, yeah, so like adding silent floor pure, so you have up to 10 or up to 22 improvement. And here as well up to 22 improvement in the impact on insulation. So it's really like important, just like here, for example, the last one, just like adding piano, it's like a strip as here, just like on the top and the bottom of the joist. So it's work as a damper. It's like absorb the energy, and you can have up to 13 points of sound transmission class up and up to 31 points of impact insulation class, which is on normal. Small details can have bigger effect as well. So here is another, like as we know, like a single CLT does not respect the standards. 26, usually in Canada, it's recommended to have IIC 50, but it's not obligatory. So here we can see that there is like an so usually the answer to have like a concrete topping and raised floor, so you can have 50. And if you want to improve the sound insulation or the impact sound insulation, just like adding those details of piano on the joist up and the bottom, and you can have 7 decibel improvement or 7 points improvement. So the last chapter of this webinar is the airtightness and the critical points. So as we know that air is an element of noise passage and heat loss. So it's really important to take care of these openings and cracks. So we can see that sealing through a gap can produce an improvement up to 24 decibel. So here's some solutions we provide. So in case of creating a mechanical, electrical plumbing, so we can use a silent pure, silent wall piton in the wall, or like when we have like an electrical enclosure. And here's example as well. There is hermic foam when we have, as we said, mechanical, electrical, plumbing penetration. So you can use a hermic foam just like to improve the sound insulation performance and decrease the passage of the sound and noise. Here another example as well. You can use a piano or silent pure or a silent floor. So there's like different products that can be used in order to improve the sound insulation and reduce the transmitted noise. So this is all the point we discussed today. And thank you for your attention. And please feel free to ask questions.
Thank you, Mohammed. It looks like as of right now, I don't see any questions in the Q&A. But as always, as we say, if you do have any questions in the next 10 minutes, hour, day, week, or month, or even in a year from now, you can always send us an email. Right on the screen, you can see it. It's eng.na@rothablast.com. I do want to remind you that we do have more webinars coming up for the remainder of this month. Next week, in particular, we have a guest speaker with us from Clemson going over the sharp metal plate. And then in the last week of October, on October 29th, we're going over innovative connections for mass timber with the radial, the ring, and the slot. So with that, we thank you and wish you a good rest of your week.